black holes, and higher compositional laws. In the STU model of string theory, so the STU model, which is a specific model of compactification involving certain field called STU, we explore the connection between extremal black holes, so those of maximum charge, and Bhairgava's higher compositional laws, which generalize the classical compositional laws of quadratic forms to higher degrees. U-duality orbits of these black holes are characterized by their charge vectors in tensor Z2, tensor Z2. By the way, that's orbits in the group theoretic sense rather than in the planetary sense. It's hypothesized that these group orbits correspond to equivalence classes of something called Bhairgava's cubes, which are numerical representations of algebraic structures containing triples of balanced-oriented ideals, which is a specific way of structuring certain subsets of rings, in rings of discriminant D. It may be that black hole microstates correspond to narrow class group classes. The narrow class group is a concept from algebraic number theory. It's a generalization of the ideal class group, which is a fundamental group associated with a ring that measures the failure of unique factorization of that ring. The Bekenstein-Hawking formula, written on screen here with delta mirroring D, escapes a full explanation, so who knows? Fun fact, Bhairgava is a genius mathematician who won the Fields Medal and grew up less than an hour away from me. Shout out to my fellow Torontonians. P.S. The STU black hole is a supersymmetric extremal solution in n equals 2, d equals 4 supergravity, characterized by 3 independent complex scalars STU. Its charge configuration is given by the integer matrix on screen here, where the electric and magnetic charges are denoted Q and P respectively, and the charge cube obtained via the tensor product Q tensor Q tensor Q yields a 6 by 6 by 6 integer tensor analogous to Bhairgava's cube of integers, which governs higher compositional laws, describing the action of the arithmetic group SL2Z on integral n-ary quadratic forms. Higher dimensional non-geometric backgrounds. What does non-geometric mean? How can you have a non-geometric space? Recall that a geometric space is one where you can have a globally well-defined notion of a metric, and that your space obeys the usual differential geometric rules, such as compatibility of coordinate patches and a defined notion of parallel transport. There are some spaces that don't have these qualities yet are spaces in their own right. Maybe they have a metric, for instance, but it's only local, not global. Maybe they have non-commutative or non-associative spatial aspects. In string theory, we explore R spaces and their R fluxes, and T-folds coming from non-trivial H fluxes. The R spaces and their associated R fluxes are related to the geometric fluxes that come about in the process of compactification. They can be understood as generalizations of torsion in the underlying geometry, and they play a role in determining the effective low-energy field theory. On the other hand, T-folds are a class of non-geometric backgrounds that come from compactifying string theory on manifolds with non-trivial H fluxes. These H fluxes are associated with the 3-form field strength H of the Neveu-Schwarz 2-form potential B. The non-trivial H fluxes can lead to interesting topological features, for example, non-geometric monodromies and non-commutative geometry, each of whom have implications for the structure of the compactified theory. The non-geometric Q flux is characterized by the formula on screen, so what role does Q flux play? Well, it bestows R spaces, their non-commutative and non-associative nature. Now the tricky part is, how do you patch in a compatible fashion these local coordinate charts? How do we go about addressing this? With something called double field theory. That embeds doubled spacetime. It merges geometric and non-geometric fluxes in this massively intertwined structure. The strong constraints shown on screen here ensure generalized diffeomorphism invariance. It's interesting that dual structures emerge over and over in physics, not just in string theory. What does this mean about reality? Algebraic K-theory. K-theory is a way to study topological invariance of vector bundles classified by Grothendieck groups K. The connections between K-theory and string theory come about when you classify D-branes. The RR, so the Ramon field strength F, exhibit quantization of the form, being members of the equivalence class, also the cohomology class, where X denotes the spacetime manifold commonly related to K-theory classes. There's a great introduction to K-theory and cobordism theory in this lecture here. This is an advanced topic. Even defining what K-theory is, what a Grothendieck group is going to take several minutes. Type 2b string theory classifies D-branes by K0 through even rank K-theory classes, while Type 2a does so by K1 via odd rank K-theory classes. In simpler terms, K-theory allows us to discern the difference between objects that can be continuously deformed into one another, much like various D-brane configurations. These ideas, as applied to physics, came about through the work of Atiyah, Witten, and Harava, among several others. For the string theoretic context we're interested in, specific supersymmetric theories, like the Witten index, a topological invariant counting BPS states, corresponds to the K-theory Euler class, where the dimension here represents the rank of the K-theory group. The Atiyah-Herzebroch spectral sequence establishes the link between K-theory and ordinary cohomology, and is an active research to this day trying to understand how D-branes behave. I'm thinking of doing an iceberg on algebraic geometry. If you would like to collaborate on it, please let me know in the comments. W strings. W-algebras extend the Virasoro algebra by incorporating higher spin currents. To account for these currents, the BRST charge has to be modified, where T is the stress-energy tensor and Cn are the ghost fields. Un are the higher spin currents, and the contour integration is over some curve C. As usual, physical states are required to satisfy the BRST condition. W strings are a different type of string, coming from W-algebras, but they have issues. Some of them being that they have negative norm states and problems with unitarity. The exact connection between alternatives of string theory, including tachyonic, baryonic, non-geometric backgrounds, and fractional strings in W-algebras isn't currently clear. The stress-energy tensor, in the context of W-algebras, provides geometric information about the worldsheet. This is at the frontier of research, even though its inception dates back to the 1980s. If you enjoyed this toe clipping, then the full video is linked in the description. You should also sign up for toe mail, which is again in the description and the pinned comment. You'll receive immediate access to all exclusive updates from the Theories of Everything podcast. It also helps me communicate directly with the core toe community. You'll also receive my top 10 toes. Think of it as the intellectual version of Quentin Tarantino's Obsession.